It's XRayBob here. This video we're going to go over power and heat units. Power is expressed in watts or kilowatts, and to calculate it you're going to multiply the current times the potential. And your current will be in amps, even if I give it to you in milliamps, convert it to amps, and your potential will be in volts or kilovolts. To get watts, you're going to have to multiply amps times volts. To get kilowatts, you can multiply amps times kilovolts. And the industry standard for comparing how fast every car goes from 0 to 60 miles an hour, how wonderful every diagnostic X-ray tube is to say what's your highest current when running at 100 kVp for an exposure of 100 milliseconds. And that'll be our power rating. And there's one more gotcha, which is if you're using single-phase equipment, you're going to scale it down by 0.7. And if you're using anything else, you can just say your power equals your current times your voltage. I show a multiplier of 1 just to help you see that the multiplier of 0.7 is used for single phase. And the reason we do that is, if you remember, single phase looks like this, feeding our circuit. And by the end of our circuit, after we've gone through our bridge diode rectifier, we have 4 diodes fully rectifying this single phase waveform such that we end up with this waveform that's going on and off as our voltage across the tube or as our radiation output from the tube. And you see we have 100% ripple. Sometimes we're at 0, sometimes we're at the desired kVp. Because it's single phase, there's a lot of wasted energy, there's a lot of low energy, there's even times when it's off. So the power on single phase is decreased, because on 3 phase, as you see, most of the time our tube voltage or our radiation output is giving us the intensity we want, the high voltage we want. So when we compare single phase and 3 phase, or 3 phase 12 pulse or 6 pulse or high frequency, we have to say that the single phase system will draw less power. So its power rating is scaled down by a factor of 0.7. So a problem might look like this: when a system with low voltage ripples energized at 100 kVp, 100 milliseconds, the maximum current is 750 mA. What's its power rating? So we would just take our current times our voltage, and because it is low voltage, because it says low voltage ripple, that's the tricky way of saying not single phase. Single phase has 100% ripple. Low voltage ripple is representative of all our other waveforms like high frequency. So I don't have to multiply by 0.7, and I just multiply on through. 3/4 of an amp times 100,000 volts gets me my 75,000 watts. Problem 2, an IR system is capable of 1500 mA when operated at 100 kVp for 250 milliseconds. What's its power rating? Again, I don't use the 250 milliseconds. That's a number in there that I'm not going to use. Doesn't that drive you nuts? You want to use all the numbers. I'm just going to use the 1500 mA and the 1500 mA, the 100 kVp. So 1500 mA is the same as 1.5 mA. And I convert my kVp to volts, 100,000, and I get 150,000 watts. Problem 3, a single phase unit at a private office reaches a maximum MA of 600 MA when operating 100 kV for 100 milliseconds. So single phases are a big tip-off here. We're going to use that 0.7 times current times voltage, and that's how we'll get not 60,000 volt amps for our answer, but 60,000 volt amps times 0.7, or 42,000 volt amps, which we call 42,000 watts. Watt. All right, so remember that. You scale it down for single phase. And wouldn't it be nice if heat units worked the same way? Well, they don't work the same way. They're kind of the opposite. So heat units, and we'll talk about heat units in reference to the anode, and we'll talk about it in reference to tube housing. And you'll do anode cooling curves and heat unit housing cooling curves in heat units. And it's the capacity to store heat, to withstand an exposure. Every exposure generates a certain number of heat units, and if you generate too much heat, your system is going to overheat. So we want to be able to control the heat units that we're going to see. Again, single phase is going to dump a lot less heat into the system than a three-phase system. Because if I say give me 100 kVp to single phase, it won't always be at 100. But this system will be a lot closer. So the same exposure techniques given in single phase will result in more heat dumping into the system when we use a higher waveform. So here with heat units, when I'm single phase, I just do kVp times MA times time. But when I'm not single phase, I have to scale it up by 1.4 to account for the additional power, the additional heat that is present because of the better waveform. So when we pull it together, we see that I got to scale power down for single phase when talking about power, and I have to scale heat units up for everything that's not single phase. So those are my magic numbers. All right, so here's a problem. How many heat units are generated by a high-frequency system when using 95 kVp, 550 mA, and 0.2 seconds? So you'll do 1.4, because it's not single phase, high frequency, times that kVp, times that mA, times that times. So here you'll end up multiplying it through, and you get 14,630 heat units. And heat units are the units for heat units. They're not watts, they're not joules, they're heat units. Another one says, all right, if I've got a maximum load, I'm a single-phase system of 30,000 heat units, could I do the following series? 5 exposures, each exposure at 120 kV, 200 mA, 0.2 seconds. So I get to use the multiplier of a 1 or no multiplier because it's single phase, and then I'll multiply my kVp, my mA, times my time. I could do this for one exposure, so 1 times 120 times 200 times 0.2, which says for one exposure I get 4,800 heat units. And if I do 5 in a row, I would do 5 times that, or 24,000 heat units. So that's how I solved the problem. But wait, they said, would it be safe to do the following series? So if I leave it here, it would be a pity. I wouldn't get full credit. So now I say, oh, the answer is yes, it would be safe. All right, number 6, our final one. If the maximum load to tube in a three-phase circuit is 50,000 HU, would it be safe to do the following series? 500 kVp exposures, each at 300 mA for 0.25 seconds, followed by one 100 kV exposure at 100 mA for 0.1 second. So we get to use our heat units. We got to use our 1.4 multiplier because it's three-phase. And let's call the first series the blue group. So 5 exposures in the blue group would be 5 times 1.4 times 100 kVp times 300 mA times 0.25 seconds, plus the red group, which would be one exposure of 1.4 times 100 kV times 100 mA times 0.1 seconds. And those two numbers would be 52.5 plus 1,400, which would add together to 53,900. So I'm done, right? I'm done. Yeah, I'm done. No, I'm not done. They said, would it be safe to do the following series? Not safe. Okay, now I'm done. All right, I want to thank Bouchon and Quinn Carroll for writing such wonderful books and creating worksheets and problems that I can share with you. This is XRayBob. I am out.